7 Distributed Databases and Client-Server Architectures. Chapter Preview. Distributed databases bring the advantages of distributed computing to the database management domain. A distributed computing system consists of a number of processing elements, not necessarily homogeneous, that are interconnected by a computer network, and that cooperate in performing certain assigned tasks. 7 Distributed Databases and Client-Server Architectures. Chapter Preview. As a general goal, distributed computing systems partition a big, unmanageable problem into smaller pieces and solve it efficiently in a coordinated manner. The economic viability of this approach stems from two reasons: more computing power is harnessed to solve a complex task, and each autonomous processing element can be managed independently to develop its own applications. 7 Distributed Databases and Client-Server Architectures. Chapter Preview. DDB technology resulted from a merger of two technologies: database technology and network and data communication technology. Computer networks allow distributed processing of data. Traditional databases, on the other hand, focus on providing centralized, controlled access to data. Distributed databases allow an integration of information and its processing by applications that may themselves be centralized or distributed. Distributed database metadata management, and other topics. However, a full-scale comprehensive DDBMS that implements the functionality and techniques proposed in DDB research never emerged as a commercially viable product. Seven Distributed Databases and Client-Server Architectures. Chapter Preview. Most major vendors redirected their efforts from developing a pure DDBMS product into developing systems based on client-server concepts, or toward developing technologies for accessing distributed heterogeneous data sources. Organizations continue to be interested in the decentralization of processing while achieving an integration of the information resources within their geographically distributed systems of databases, applications, and users. Contents. Distributed database concepts. Data fragmentation, replication, and allocation techniques. For distributed database design. Types of distributed database systems. Query processing in distributed databases. Overview of concurrency control and recovery in distributed databases. An overview of three-tier client-server architecture. Distributed databases in Oracle. A distributed database, DDB, as a collection of multiple logically interrelated databases distributed over a computer network, and a distributed database management system, DDBMS, as a software system that manages a distributed database while making the distribution transparent to the user. Distributed databases are different from Internet web files. Web pages are basically a very large collection of files stored on different nodes in a network, the Internet, with interrelationships among the files represented via hyperlinks. The common functions of database management, including uniform query processing and transaction processing, do not apply to this scenario yet. The technology is, however, moving in a direction such that distributed World Wide Web, WWW, databases will become a reality in the future. The proliferation of data at millions of websites in various forms does not qualify as a DDB by the definition given earlier. Contents. Parallel versus distributed technology. Advantages of distributed databases. Additional functions of distributed databases. There are two main types of multiprocessor architectures that are commonplace. Shared memory, tightly coupled, architecture. Shared disk, loosely coupled, architecture. Shared memory architecture, multiple processors share secondary storage and also share primary memory. Shared disk architecture, multiple processors share secondary storage but each has their own primary memory. These architectures enable processors to communicate without the overhead of exchanging messages over a network. Database management systems developed using the above types of architectures are termed parallel database management systems rather than DDBMS, since they utilize parallel processor technology. Another type of multiprocessor architecture is called shared nothing architecture. In this architecture, every processor has its own primary and secondary memory, no common memory exists, and the processors communicate over a high-speed interconnection network, bus or switch. Although the shared nothing architecture resembles a distributed database computing environment, major differences exist in the mode of operation. Contents. Parallel versus distributed technology. Advantages of distributed databases. Additional functions of distributed databases. Distributed database management has been proposed for various reasons ranging from organizational decentralization and economical processing to greater autonomy. Some of these advantages are management of distributed data with different levels of transparency, increased reliability and availability, improved performance, easier expansion. Management of distributed data with different levels of transparency. Ideally, a DBMS should be distribution transparent in the sense of hiding the details of where each file, table, relation, is physically stored within the system. Distribution or network transparency. Replication transparency. Fragmentation transparency. The following types of transparencies are possible. Distribution or network transparency, this refers to freedom for the user from the operational details of the network. It may be divided into location transparency and naming transparency. Location transparency refers to the fact that the command used to perform a task is independent of the location of data and the location of the system where the command was issued. The following types of transparencies are possible. Naming transparency implies that once a name is specified, the named objects can be accessed unambiguously without additional specification. Replication transparency, copies of data may be stored at multiple sites for better availability, performance, and reliability. Replication transparency makes the user unaware of the existence of copies. The following types of transparencies are possible. Fragmentation transparency. Two types of fragmentation are possible. Horizontal fragmentation distributes a relation into sets of tuples, rows. Vertical fragmentation distributes a relation into subrelations where each subrelation is defined by a subset of the columns of the original relation. The following types of transparencies are possible. A global query by the user must be transformed into several fragment queries. Fragmentation transparency makes the user unaware of the existence of fragments. To increased reliability and availability, these are two of the most common potential advantages cited for distributed databases. The following types of transparencies are possible. Reliability is broadly defined as the probability that a system is running, not down, at a certain time point, whereas availability is the probability that the system is continuously available during a time interval. When the data and DBMS software are distributed over several sites, one site may fail while other sites continue to operate. The following types of transparencies are possible. Only the data and software that exist at the failed site cannot be accessed. This improves both reliability and availability. 3. Improved performance. A distributed DBMS fragments the database by keeping the data closer to where it is needed most. Data localization reduces the contention for CPU and I/O services and simultaneously reduces access delays involved in wide area networks. The following types of transparencies are possible. When a large database is distributed over multiple sites. Smaller databases exist at each site. As a result, local queries and transactions accessing data at a single site have better performance because of the smaller local databases. In addition, each site has a smaller number of transactions executing than if all transactions are submitted to a single centralized database. The following types of transparencies are possible. Moreover, interquery and intraquery parallelism can be achieved by executing multiple queries at different sites, or by breaking up a query into a number of subqueries that execute in parallel. This contributes to improved performance. For easier expansion, in a distributed environment, expansion of the system in terms of adding more data, increasing database sizes, or adding more processors is much easier. Contents. Parallel versus distributed technology. Advantages of distributed databases. Additional functions of distributed databases. Distribution leads to increased complexity in the system design and implementation. To achieve the potential advantages listed previously, the DDBMS software must be able to provide the following functions in addition to those of a centralized DBMS. Keeping track of data, the ability to keep track of the data distribution, fragmentation, and replication by expanding the DDBMS catalog. Distributed query processing, the ability to access remote sites and transmit queries and data among the various sites via a communication network. Distributed transaction management, the ability to devise execution strategies for queries and transactions that access data from more than one site and to synchronize the access to distributed data and maintain integrity of the overall database. Replicated data management, the ability to decide which copy of a replicated data item to access and to maintain the consistency of copies of a replicated data item. Distributed database recovery, the ability to recover from individual site crashes and from new types of failures such as the failure of a communication links. Security, distributed transactions must be executed with the proper management of the security of the data and the authorization/access privileges of users. Replicated data management, the ability to decide which copy of a replicated data item to access and to maintain the consistency of copies of a replicated data item. Distributed database recovery, the ability to recover from individual site crashes and from new types of failures such as the failure of a communication links. Security, distributed transactions must be executed with the proper management of the security of the data and the authorization/access privileges of users. Distributed directory, catalog, management, a directory contains information, metadata, about data in the database. The directory may be global for the entire DDB, or local for each site. The placement and distribution of the directory are design and policy issues. Contents. Distributed database concepts. Data fragmentation, replication, and allocation techniques for distributed database design. Types of distributed database systems. Query processing in distributed databases. Overview of concurrency control and recovery in distributed databases. An overview of three-tier client-server architecture. Distributed databases in Oracle. 7.2 Data fragmentation, replication, and allocation techniques for distributed database design. The database is divided into logical units, called fragments, which may be assigned for storage at the various sites. Data replication permits certain data to be stored in more than one site. These techniques are used during the process of distributed database design. 7.2 Data fragmentation, replication, and allocation techniques for distributed database design. Contents. Data fragmentation. Data replication and allocation. Example of fragmentation, allocation, and replication. In a DDB, decisions must be made regarding which site should be used to store which portions of the database. Before deciding how to distribute the data, must determine the logical units of the database that are to be distributed. The simplest logical units are the relations themselves, that is, each whole relation is to be stored at a particular site. X, a site to store each of the relations employee, department, project, works _on, and dependent. In many cases, a relation can be divided into smaller logical units for distribution. X, user may want to store the database information relating to each department at the computer site for that department. A technique called horizontal fragmentation can partition each relation by department. Assume that here are 3 computer sites, one site for each department in the company. Contents. Horizontal fragmentation. Vertical fragmentation. Mixed, hybrid, fragmentation. A horizontal fragment of a relation is a subset of the tuples in that relation. The tuples that belong to the horizontal fragment are specified by a condition on one or more attributes of the relation. Often, only a single attribute is involved. X, define 3 horizontal fragments on employee relation with conditions, dno equals 5, dno equals 4, and dno equals 1. Each fragment contains the employee tuples working for a particular department. Similarly, we may define 3 horizontal fragments for the project relation, with the conditions, dnum equals 5, dnum equals 4, and dnum equals 1. Each fragment contains the project tuples controlled by a particular department. Horizontal fragmentation divides a relation horizontally by grouping rows to create subsets of tuples, where each subset has a certain logical meaning. Contents. Horizontal fragmentation. Vertical fragmentation. Mixed, hybrid, fragmentation. Each site may not need all the attributes of a relation, which would indicate the need for a different type of fragmentation. Vertical columns. A vertical fragment of a relation keeps only certain attributes of the relation. X, we may want to fragment the employee relation into 2 vertical fragments. The first fragment includes personal information, name, date, address, and sex, and the second includes work, related information, SSN, salary, super_SSN, and DINO. It is necessary to include the primary key or some candidate key attribute in every vertical fragment so that the full relation can be reconstructed from the fragments. Hence, we must add the SSN attribute to the personal information fragment. Note, each horizontal fragment on a relation R can be specified in the relational algebra by a psi-R operation. A set of horizontal fragments whose conditions C1, C2, Cn include all the tuples in R, that is, every tuple in R satisfies C1 or C2 or Cn, is called a complete horizontal fragmentation of R. A vertical fragment on a relation R can be specified by a Li-R operation in the relational algebra. A set of vertical fragments whose projection lists L1, L2, Ln include all the attributes in R but share only the primary key attribute of R is called a complete vertical fragmentation of R. Contents: horizontal fragmentation, vertical fragmentation, mixed, hybrid, fragmentation. We can intermix the two types of fragmentation, yielding a mixed fragmentation. X. Combine the horizontal and vertical fragmentations of the employee relation into a mixed fragmentation that includes 6 fragments. In this case, the original relation can be reconstructed by applying union and outer union, or outer join, operations in the appropriate order. A fragment of a relation R can be specified by a select project combination of operations pi L, sigma C, R. A fragmentation schema of a database is a definition of a set of fragments that includes all attributes and tuples in the database and satisfies the condition that the whole database can be reconstructed from the fragments by applying some sequence of outer union, or outer join, and union operations. An allocation schema describes the allocation of fragments to sites of the DDBS. Hence, it is a mapping that specifies for each fragment the site, S, at which it is stored. If a fragment is stored at more than one site, it is said to be replicated. (7.2) Data fragmentation, replication, and allocation techniques for distributed database design. Contents: data fragmentation, data replication and allocation. Example of fragmentation, allocation, and replication. Replication is useful in improving the availability of data. The most extreme case is replication of the whole database at every site in the distributed system, thus creating a fully replicated distributed database. This can improve availability remarkably because the system can continue to operate as long as at least one site is up. It also improves performance of retrieval for global queries because the results of such queries can be obtained locally from any one site. Hence, a retrieval query can be processed at the local site where it is submitted, if that site includes a server module. The disadvantage of full replication is that it can slow down update operations drastically, since a single logical update must be performed on every copy of the database to keep the copies consistent. This is especially true if many copies of the database exist. The other extreme from full replication involves having no replication, that is, each fragment is stored at exactly one site. This is also called non-redundant allocation. Between these two extremes, we have a wide spectrum of partial replication of the data, that is, some fragments of the database may be replicated whereas others may not. The number of copies of each fragment can range from 1 up to the total number of sites in the distributed system. A description of the replication of fragments is sometimes called a replication schema. Each fragment, or each copy of a fragment, must be assigned to a particular site in the distributed system. This process is called data distribution. The choice of sites and the degree of replication depend on the performance and availability goals of the system and on the types and frequencies of transactions submitted at each site. Data fragmentation, replication, and allocation techniques for distributed database design. Contents: data fragmentation, data replication and allocation. Example of fragmentation, allocation, and replication.